hey everyone. Thanks for having me today. Thanks, Ralph, for the nice intro. I want to talk about today about our most advanced image model family, FLUX, and I want to explain you the concepts you really need to understand how it works. I think Raul already has said a lot about me, so I'm Andy, I'm a co-founder of Black Forest Labs. We are the company behind the well-known FLUX model family. And at BFL, we believe that visual media will be the central interface for human communication in the future. And our mission or our vision is to become the central infrastructure provider to power all the human communication through that visual media in the future, not only what cameras can do, but way beyond that. With that mission in mind, we've incorporated the company in April 2024 and launched it in August 2024. We've grown it since to 40 full-time employees that are distributed among 2 headquarters. Our main office is in Freiburg in Germany, actually in the Black Forest. And we also opened an office earlier this year in San Francisco. So we've launched our first model family, the FLUX model family, at the day when we launched the company. And since then, we've mainly structured our releases in 3 tiers. I just want to share a bit light on those. So we have the FLUX Pro models. Those are our best, most advanced, highest quality, and fastest models, and they are only available via the BFL API. They are just enterprise grade, and you can scale from 0 to massive volumes in, nearly instantly and without any infra hassle. As some of you might know, my co-founders and me, we've been the original developers behind latent diffusion and stable diffusion. So we've still very strong roots in the open source community. And that's why we also still are publishing openly available models. Also here in 2 tiers, we have the FLUX Dev models that are open weights. These are available for everyone, downloadable on Hugging Face basically. They are self-hostable, so perfect for someone who wants to host a text-to-image model in their own infrastructure, and they are fully customizable, so you can fine-tune them to any extent, and in fact, they actually have by now a huge ecosystem attached to them of LoRa's, of fine-tunes, like a lot of stuff going on in the open source community. Super nice to see this. And finally, we have the fully open source FLUX Schnell model. This is super fast and ultra lightweight, and it's basically the perfect entry point into the FLUX ecosystem. And if you talk about the ecosystem, we can look at the model atlas on Hugging Face here, which basically shows all the ecosystem, meaning fine-tunes and stuff around the most important foundation models across domains. And guess which single model has the largest ecosystem attached to it? It's actually our FLUX Dev model. So you see that we already shape, I think, the image generation space in the open source community very heavily. And as said, our vision is really to advance this further to become the central provider of images and videos that humans will communicate with in the future. All right, that much to the company. Let's now come to the core part of the talk. How to unify text-to-image generation and image editing. Why is that important? I think, first of all, image generation has made huge leaps in the past 5 years. We've been really at the forefront of this, I think. But image editing has, since very recently, not really kept up with this speed of advancement in image generation. I would argue that image editing is at least equally, if not more important than text-to-image generation, because it allows us to iterate over content multiple times and gradually refine it. I'll show you what that means in a second. And by that, it just gives us much more control over the output. Whoever has professionally worked with images, I think, will totally understand what I mean here. So I think that's why it's a very interesting and important problem to solve. And with FLUX Kontext that we released in June 2025, so earlier this year, we published the first diffusion model or flow matching model that combined text-to-image generation and editing. And that really unlocked new properties that we have not seen before, things like character consistency, style reference, local and global editing, everything within one model, available within seconds once you prompt it, so at really high speeds. And I think the top row of images here that I brought to you pretty much visualizes this. So we start here at the right part here with this image. We remove the object from her face. We keep the character then and transform it into a completely new scene. So in this case, this inner city. And in the rightmost example, we just change it to a winter scene. This is all possible within single seconds, and arguably whoever has used Photoshop before, this took just very long in Photoshop before we released this model, right? So here are a couple of more examples. Style transfer is really nice. So here at the left example, we just take the input image and transform transfer the style of it to a new prompt, basically, to new content, or we can do fun things like text editing. Here we changed in the right example, Montreal to Freiburg, while keeping the font exactly the same. Importantly, Flux Kontext also solves a lot of interesting business problems. So we can actually get from an in the wild image of this skirt to a full-blown product shot within a couple of seconds, or on the right side, we see that we can transform a simple sketch into a full-blown render also in a matter of seconds. So let's look a bit more at the pipeline and how image generation is different from image editing. Let's start with a classic image generation or text-to-image generation pipeline. We just use a prompt that describes a scene. We push it through the network, and we arrive at an image that hopefully follows that prompt. In this case, it does, I think. For image editing, it's quite a bit different. Here we start with an image, and instead of describing a whole scene that we want to generate, we only describe what I now call an instruction text prompt that actually tells the model how it should change the initial image. So here I say, convert this to a Lego scene, and we get the image of this church as a Lego scene. This all, again, in a matter of seconds. Combining these two aspects in a single model is super important because it just gets rid of very manual fine-tunes that we had to do before or complex workflows. So this is, again, text-to-image generation and text-based generative image editing combined in one model, and we don't need to fine-tune anymore or add workflows, which was the primary means to get to these editing capabilities before we released the model. All right, I think this gives a bit of a glimpse of the impact. I'll also show you a live demo of the model later. Now I really want to dive into how this model actually works. And in order to understand this, we have to look at an algorithm that's called Latent Flow Matching, which is defined based on two concepts. It's latent and flow matching, and I want to share light on these two concepts because these are really important to understand how the model works. So let's start with latent. This comes from the algorithm latent generative modeling that me and my co-founders invented 5 years ago while we still were students at the university. And to start with, I just want to show you these two images. The left one is a JPEG image, which is an approximation of the right one, which is a PNG image. I would say these images look exactly the same, but if you look at the file size, we see something remarkable, I think. The JPEG image is actually 10 times, or like close to 10 times, or close to an order of magnitude smaller than the PNG. So apparently, we can remove a lot of information without actually noticing it. And this is very interesting. And we can even visualize it a bit more differently if we plot the perceptual similarity of an approximation of an image, in the last example, the JPEG, and the original image, in the last example, the PNG. Against the file size, we get a plot that looks conceptually quite like this. So we have here on the left side that the perceptual similarity quickly increases with file size, but then stays very, very constant. You might ask, okay, what does this now have to do with generative modeling? This actually has to do a lot with generative modeling because it shows us that when we train the model on a perceptual signal, like an image, for that image to look real, you don't need to model all the high frequency, imperceptible details. So this part, this flat part of the curve, because here we don't increase the perceptual similarity anymore. This doesn't actually matter to our eye, and training on this would just be a great waste of compute and time. So we should not do this. And this is at the core of latent generative modeling. We really want to find a representation of an image that only contains those details in an image that actually matter to us. And this is how we do it. We train, well, we call this representation latent space. This is why the term latent generative modeling comes from, so generative modeling in the latent space. And this is how we train the pipeline. We train a so-called autoencoder to extract that latent space before we train the actual generative model. And it works like this. We start here on the left side with an input image, push this through a CNN encoder, extract that latent representation, where we will later train the generative model on, and then we apply an operation that's called regularization. This forces the model to discard information from this latent representation. It can be done either discrete or continuous. We mostly use continuous operations here, and then we push it again through a decoder to reconstruct the original image. And we train this model end to end, so we use a reconstruction loss that just minimizes the difference between the reconstructed and the input image. And importantly, we add this here on the top right, this discriminator loss that is basically a prior to the human perception. This one takes care that the details that are contained in the image are actually only those that matter to our perception. And like this, we can arrive at this latent space that really only contains those details that matter to us. So this is the first part, and once we've done this, we train the generative algorithm to generate images from basically easy and tractable distributions. I come to this in the next slide. So, and this algorithm is called flow matching. Flow matching is a general family of algorithms that wants to find a vector field which is parameterized by a neural network that maps from a simple distribution. This is here visualized on the right side, so here, which is always the normal distribution, to a very complex and unknown distribution, which is our natural distribution of images. This is visualized here. So this is again in the latent space happening. I just explained this. We have the encoder to encode here, and we model everything in the latent space. So we want to learn a vector field that is parameterized by a neural network. And flow matching actually gives us a super simple algorithm to learn this. All we do is we couple each sample from our data distribution with a random sample from our normal distribution, so say this one, and we just repeat this for every sample in the data set. And like this, we can construct a artificial vector field. This is obviously, this looks really wrong, because in a vector field, trajectories can never cross. Otherwise, it's by definition not a vector field. The interesting thing with flow matching is, if I just do this and train the model to approximate this horribly wrong vector field, I end up with a true vector field, actually. So if I do this very often, the model in the end approximates the true vector field where we see that trajectories don't cross. This is the flow matching algorithm. And obviously, since we want to control the output based on text prompts, we condition our deep neural network always on those text prompts to be able to control it later. And once we sample the model, so say now we've learned this vector field, the network represents it. Once we sample from it, we just apply the vector field step by step in a numerical integration scheme. So we start with a sample from the easy and tractable distribution, from the normal distribution, and just apply a numerical integration scheme where each integration step is actually a forward pass of the neural network. And like this, in 50 steps, in more or less, we arrive then from a sample from this easy distribution at a sample from the data distribution that we then again push through the decoder, and we arrive at a generated image in the end. So this is the flow matching algorithm combined with this latent generative modeling. All right, so this is how you can generate images based on text. But now how does this apply to Flux Kontext? Because that also can do image editing, right? We do this with a very simple trick, I would say. I want to share a bit about the architecture of the model. So we train a general transformer model, which is the backbone of what we're doing for the Flux models. And we condition that. This is the same for image editing and text-to-image generation on a text prompt. This is here on the top left part here. But instead of only conditioning on one image that we want to generate, we condition on an additional image that is now the context image for the model. So we here have two images. We push them through the latent space, and in the latent space, we form a sequence of tokens. We have text tokens and we have image tokens for the two images, the one we want to generate and the one that is our context image. And we handle this token stream with a transformer architecture, which is composed of double stream blocks, where we have domain experts for the visual and the text tokens, and then classic transformer blocks that are just handling all the tokens similarly. And this is how we parameterize our network. And we can just change from text to image generation to image editing by using or removing this context image. So if we do a text to image generation, we just remove that image. So this is how it works, just a conditioning trick in the end. Last question I want to answer, how is it so fast? I think whoever knows the Flux models knows that they are pretty fast. What do I mean when I say fast? They are up to an order of magnitude faster than the competition. So we see the Flux models here on the left side of each plot, and this is both for image editing and image generation. So they are always on the left side, and say for image generation, we are 25 times faster than GPT-1 image, for instance. We are still for image editing up to 10 times faster than the slowest competitive model. So how is that possible? And the algorithm that powers this is called Adversarial Diffusion Distillation. Here, the goal is to bring down the number of numerical integration steps. If you remember, I said these were 50 for trained models, or more or less 50 as a rule of thumb, down to as little as 4. And in order to do this, we do two things. We take a pre-trained flow matching model and initialize two neural networks from it. First, the teacher, you see it here on the bottom part of the plot, which is just this model itself. And then we initialize another new model, the student. The student should learn to generate images that are as good as the teacher images, but only in 4 steps. This is the goal, and here's how we do it. We start with an image again, encode it into the latent space, and then we use the student. This is visualized here on the top part. We use the student to basically generate this image or generate a generated image from it in 4 steps. Then we arrive here at the top right side at an image that in the beginning, when I start training this, is very blurry and looks very unrealistic. And I want to improve these images as much as possible. How do I do this? We use this generated image from the student, push it again through the encoder, and do the same generation procedure with a teacher. But here I use 50 steps and I arrive at a very faithful and nicely looking image. And we just train a distillation loss that compares the images of the student with the images of the teacher and pushes the student to follow the teacher distribution. This alone is not enough, which is why we add another loss on top of it, which is visualized in the bottom left part and initialized with a feature extractor called DynoV2. This is a discriminator loss, which is again a prior to human perception. This takes care that the images that the student creates are actually following or perceptually pleasantly looking for us humans. So again, they make really sharp edges for the student images and make them realistically looking in the end. So this is super nice, and we can, with this algorithm, we can get down the number of numerical integration steps from 50 to 4, which is great, but it's very complicated. It's like 2 times encoding. So we see here in the top row, we see an encoding operation. Also in the bottom row, we see an encoding operation, and same 2 times decoding. So it's super tedious to train this and very computationally heavy. And this makes us arrive at the final algorithm that we actually use to train the Flux model. It's the latent adversarial diffusion distillation. You know now what latent generative modeling is, so I guess you know the motivation behind this. We just want to get rid of all the encoding and decoding, and we want to put the entire algorithm in the latent space. And this is what the latent adversarial diffusion distillation algorithm does. It just does exactly the same thing than the last algorithm, but it applies it completely in latent space. And for that, we change two things. We replace this dino, I go back once to see it, this kind of discriminator loss, this feature extractor, with the teacher itself. So we use the pre-trained model to as the prior to calculate this adversarial loss, and we throw away the distillation loss completely. By that, we can actually achieve much less compute efforts. Does this work? Yes. Much less compute efforts, and can speed up the algorithm a lot. So in a nutshell, latent adversarial diffusion distillation is just the adversarial diffusion distillation applied to the latent space. And by that, we can actually bring down the number of integration steps from 50 to 4, which is again this order of magnitude speed up that we've seen in the plots. So here we get a 12.5 times speed up. All right, now you know why it's so fast. And as a final, I think, thing that I want to show you, I have brought a short demo to you to actually see how the model works. So let's maybe use this image. Here we have an image of my favorite football club, the SC Freiburg, which is the local football club in Freiburg. And we can now just play around with this motif. So we say, put this logo onto a t-shirt. Oops. All right. Here we go. Hope internet is okay. Yes. Cool. Then we wait for a couple of seconds. And what we get is live demo. Nice, okay. Now we're hot. I think now it should be faster. This was too slow for Flux normally. So now we get this nice picture of the logo onto an image. The nice thing now is I can use this image and iterate over it. This is why I think editing is super exciting. So now I can say, okay, this logo is too large. Make the logo smaller and put it on the top right part of the t-shirt. Again, we submit here. And here's what I get. Again, 4 images, and I can just go on like this. Let's make the t-shirt red. And I think as the next thing, I want to do something more challenging. Let's put this t-shirt onto a human and transform them into the wild, because so far we've done like somewhat local image edits. Let's do something more global. Oops. Oh, in the park. All right. I'm now generating 2 examples. I don't know what's happening here. Okay, par also. Model could infer what I wanted to do. That's great. So nice. Here also good. Let's use her, and one final edit maybe. So this was a global transformation, which is nice. And now let's, as an example of style transfer, make this a watercolor painting. As the final one. Come on, last one. Ah, nice, cool. And here we go. Now we could print it out and place it on I don't know, take it at home, whatever. No, I think the general thing is coming across. It's very powerful, very flexible, and I think this was it with this demo. I want to say thank you. We are hiring. Come visit our booth. We're just right next to the main stage here. We have a lot of openings, so if you're interested in what we're doing, please apply, or visit our playground. This is where I basically just demonstrated the model. Thank you so much, and have a great conference.